Okay, that sounds pretty good. We know what the normal is. Let me turn. Is the normal is any mark perpendicular to a surface. Now, I'm just going to repeat that a little bit more, make sure we understand it. I'm going to draw some lines one more time. Okay, let's draw this line. Here's a line right there. Now I'm going to draw a normal to it. I'm going to pick a point, and I'm going to draw a normal to it. Let's see. Let's use this one again, and I'm going to pick that point right there. So here would be the normal to that point. There it is, 90 degrees. Okay. How about this point over here, right there? I'm going to pick a normal to that point. Okay, there it is, 90 degrees. When I say 90 degrees, I mean that this forms a 90-degree mark right here. This is 90, and of course this is 90. All the way around, it's going to look like 90, right? Hope we all know that. And all these form 90. And once again, it makes no difference what the shape of the object is. What do you mean it makes no difference what the shape of the object is? Well, let's see. Let me get rid of this a second. If we can. Okay, and let's make that shape look like this. Let's see, let's draw a shape, and let's draw a shape that looks like this. There it is. Great. Now let's draw a line. And we want to find some 90-degree points. Okay, let's find I'll just put the points there for now. There's one right there. Okay, this time we'll do it in blue. Let's pick one there. And let's pick a point there. And I'm going to draw normals to all these points. And this could have been a circle as well. Because to the circle, there's still a 90-degree mark that goes down right through it at 90 degrees, if we so choose. So let's, matter of fact, let's draw a circle as well. Let's see, draw shapes. There's a circle. I'll put that circle there. Okay. Let's go back to our pen. And let's do a nice bright red. So a normal to this point would be like that. A normal to this point would be like that. A normal to this point right over here would be like that. A normal to this point would be like so. Hope you're kind of getting the idea. And if I choose a point over here, someone said, hey, could you draw a normal to that point? Sure, I can. It's going to look like this. Oh, missed the point. Right there. How about right here? Can I draw a normal to that point? Sure, I can. There's, well, 90 degrees. Always forming a nice 90 degrees to the surface. So once again, this is 90, and there's a 90 right here. All the way around, these are forming 90s. 90 there, 90 here. Always forming 90s. Okay, let's go on. We got this idea of normal being a perpendicular line to a surface. Now let's go, and I'll tell you what. Let's draw. Everybody likes pool. Let's make a pool table here. Draw a line. Let's draw a shape, and let's make that shape like this. There it is. There's our pool table. Okay. And in our pool table, of course, what good is a pool table without a ball? There's our ball. Now, I'm going to hit that ball, and I want that ball. I want that ball to go like so. I want that ball to come and hit the pool table right there. Okay? Well, the next thing I really ought to do is if that's the point where it's hitting right here, I want to draw a normal to that point. So let's do that. Control 5. Let's see. I want to draw a nice big old green normal. And that big old green normal is going to be right like that, pretty much. Okay? Go just a tad here if I can. Okay, just a little bit over. Easier said than done here. There we go. All right. Sometimes you can't draw. I'll just draw the light ray so it hits right there again. Okay, so the light ray is coming in. The green is our normal. The black is the motion of our red ball. Okay. Now, where is the angle in? The angle in is not measured to the surface. It's not measured to the end of the pool table where it's hitting right here. Let me show you what that looks like. Here's the pool table surface right here. That's the pool table surface. It's not measured to there. It is measured to the normal. So let's say this is coming in at 60 degrees right here. This is our angle in. Angle I. Okay, that's our symbol for our angle, and that's the angle in. It's measured to here. Okay. Now, we know that the angle out is going to be the same thing. So I'm going to show that same angle out now. I'm going to show that same 60 degrees, but now it's going to be coming out. Let's see. Here's that guy. It's going to be coming out at about the same thing. And it's going to hit about there. So it looks like the angle out is going to equal the angle in. And I'm going to draw, this is the angle out. It's a symbol for angle. In case I didn't mention it before, you should have gotten it from class. This is the symbol for angle. Well, here's the angle out right here. Angle of reflection, we're just going to call it angle O to make it easier. The angle out is also going to be equal to 60 degrees. Measure between those 2 points. Note that we did not measure it to the surface. Now, while we got this picture here, I want to kind of break out 2 little sections. I want to break out this section right over here, going from here down to here. Okay? Okay, from there to there, of the pool table. And I just want to show you real quick that this kind of forms a reflector, like the same kind of reflector on a bike or on a car. And let me show you why. Let me show you why that is. I'm going to take a line coming in. Here's our angle coming in. There's our ball. Let's say the ball is coming in like this. There it is. Okay. Here's our normal right there. So we know it's going to bounce out about the same way it came in. Okay, like so. And when it hits, there's our normal at this point right there. And this guy's going to bounce back in the same direction it came. So you can imagine this is a ball. That's exactly how it's going to go. And it's going to end up bouncing like so. Anybody who's played pool kind of gets an idea for this. Okay, this angle right here, look for the dot, that angle right there, that angle equals this angle. And this angle right over here equals this angle. It forms a reflector. So if you hit the ball like this is at a 90 degrees. So the pool table, you're hitting it toward the corner, the ball comes in like so and bounces out just the same way. Try it. Okay, in class we did a much better picture. It's a little hard to do it here on this small little surface, but you get the idea. That reflectors are formed by, actually they're pyramids, but I can't draw a pyramid very well, so I just use a flat surface, 90 degrees. A 90-degree surface, light coming in, pardon my poor picture, bounces out the same way it came in. This is 90 degrees right there. You can look at it as a surface, a mirrored surface. Light comes in, bounces across, and goes out the same way it came in. Just remember, if you are asked to draw it on a quiz, you must draw, pick this, you must draw the normal, which in this case would be right through there like that. Okay? And this one would be right like this, 90 degrees to that surface. Okay? 90 degrees and 90 degrees, two normals. Again, much better picture in class, a little hard to do with this little pen and pencil, but you get the idea. And your notes, this is intended to supplement your notes, so you should see all this stuff in your notes anyway. Okay, so let's keep going here. Let's assume that we have a mirror. This is a flat mirror called a plane mirror. And just so we know what side we're looking at, here is the mirrored surface right there. That's the mirror part. Oh boy, that doesn't look like mirror, does it? Mirror. Hard to write with this little pen. Okay, that's the mirror. And over here is our little man. Okay? Obviously a man. Okay, now, here's what we have to establish with plane mirrors. First, there's a couple of things that you should know. If you look at a plane mirror, and you can stop this video and go look in the mirror if you'd like, but you're going to find that if you're looking in the mirror, the image that you're going to see in the mirror, the distance in front of the mirror, we'll just call that DI in front, okay, from here to here. If you look in that mirror, you're going to see yourself in back at about the same distance. Matter of fact, not about, at exactly the same distance. So let's just call this the distance of the reflection. So if you are 2 feet in front, you are 2 feet in back of your mirror. Okay, that's rule number 1, and it's pretty easy to prove that rule. Okay, so number 2, let's assume that for now, what we're trying to do is we are trying to figure out where the image is going to be. Okay, now the image is the reflected part. I'm just going to write on this side of the mirror, image. Now don't forget, the reason I'm drawing it on this side is that's where it appears to be when you are looking with your eye toward that point. In the mirror, the image seems to be on the other side. And just so we could establish some rules, let's call you the object. Okay, and we'll use these terms all the way through. So if here's the object, the image is on the other side of the mirror. But how do you know exactly where it is? Well, let's assume that you're looking at your toe. Now, we said in class when we talked about light in general, that the reason we see, let's just change this color, the reason we can see this toe over here is that light is reflected off it. Light does not come from your eye, it comes from the thing you're looking at. And the reason you can see your toe is it's reflected. And in this case, it's going to be reflected in the mirror. But the question that we're trying to determine is how is it reflected? And how, based upon that reflection, do we establish where the image is? So let's see. We know there's one rule we've been using all along in this little tutorial, and that is the angle in equals the angle out when measured to the normal. And don't forget, we wrote the word normal, N-O-R-M-A, and a big old L over here, because I wanted you to remember this was a 90 degrees. 90 degree to a surface, that's what the normal is. All right, now I've got to establish, if the light's coming from here, and it's going up to his eyeball right here, I got to try and establish where the normal is going to be. And since the angle in is going to equal the angle out, I'm going to put it, I'm going to say that normal is going to be right about here. Okay, and matter of fact, I'm going to draw that normal right there. I purposely made it about halfway from his eye to his toe. So if his eye was up here and his toe is down here, this is about halfway, and now I'm going to draw a normal. Let's see, we got to draw, let's make it a line, control. Let's use that same old big green that we had before. Let's choose a dotted line this time. Okay. There's a normal. Notice I drew it right through the surface, right through the mirror. And now the next thing I'm going to do is I'm going to draw another line. Let's see, let's keep this a solid line. Make it look like this. It's going to be coming from his foot, and it's going to be hitting right at that point. Okay? So our angle in looks like this. Our angle in looks like, I'm going to say it's about 45 degrees here. 45 degrees. That is our angle. And remember I told you I was going to start using just angle I for angle in. Well, okay. If it comes in that way, well, guess which way it's going to bounce out. If it bounces out, I said 45. It's not quite 45, but you're going to get the idea. Okay. It's going to bounce out at the very same angle it came in at. Okay. So if that was 45, it would mean that this angle right here is also 45 degrees. Looks like a little less than that, but you get the idea that the angle in equals the angle out, and the light is coming from his foot, not from his eye. Here's the arrow showing how the light is going. Well, okay. The light's bouncing up like that, but what does that mean? Well, it means he's seeing his toe based upon this reflected light right here bouncing off his toe. And what we have to do is we're going to flip one of these lines. But which line to flip? Now, in class, remember I told you when we have an arrow, I was going to make a funny rule. Okay, I called the arrows. I said they have a nose. Okay, a nose. Right there. That's the nose. And I said they had a butt. Just going to put down B for butt. And we're going to flip the one so that when we flip this, we're going to have establish a butt-to-butt relationship. I'll show you what that means in a second. Let's see. Let's see. I'm going to use the same arrow bouncing back now. Oh, by the way, we already know. I'll label this in a second. So the light bouncing back, I'm going to show as a dotted line again. But I'm going to show it bouncing back like so. I just flipped this guy right over. All I did is flip him. I'll show you what I mean by that. I took this line right here, stuck right there, and I flipped this all the way over till it ended up like this. Now when I did, that red arrow, this red arrow right here, okay, ended up looking like this. Okay. Here's the butt of that arrow. Remember I told you the flat part was the butt? Okay, so the flat part was the butt. And here was the butt of this one. If I flip it right over, it's butt to butt. And I know, I said before, that the distance in back was equal to the distance in front. Just extend this a little further. Okay, I'm going to move this just a little further out, like so. And it turns out that if the distances are the same, then our image, which is what we're looking for, our image in green, where are you, green, ought to be right here. So this is where the toe ought to be. I'll kind of start to draw this up. Now we only looked at the toe, but it works for every other point. It works for every other point. And all I did, let me straighten this out a little bit more. All I did, that's a little better. All I did is let me get this guy over there. All I did is flip him like this. Okay, there. All I did is flip them over. It's not the best drawing in the world, but the distances in back are the same in front. And if I did it for every point, if I did exactly what I did now for every point, okay, we would end up with the very same image, here's his head, as we're seeing on the other side. Now, I've done this in class, so pardon my crummy drawing here. It's a little hard with this little tablet, as I said. But all I did, and you know, as I told you, I took this line, and I realized that the reflection, I took the one with the butt, and I flipped that over, and I made it a straight line on this side. So this and this are simply flipped, and that establishes where the toe is going to be. And I can do this for every point. Let's do it for one more point, and we'll see if it makes sense. Okay, in the last picture I showed you the reflection in and out. The angles were equal. And we established where this person's reflection was with respect, assuming that he was looking at his toe. In other words, this point right over here, looking at this point right over here. And we showed the angles bouncing up. Now let's assume that we want to see where his belly button is. That's right here. And I told you that we can do this for every point. And don't forget, all these lines, there's an infinite number of light rays. We just need to see one to establish where it's going to be. Our rules are that the distance in back is going to be equal to the distance in front of the mirror. We call that distance in front before. So let's see. This time, we're looking at his belly button. Light's going to be coming from that belly button. And I'm going to say about halfway up is about right there, because I want to establish, get this kind of right so that the angle in equals the angle out. So I'm saying our normal is going to be right about here. I'm doing it red this time. And we'll label it with N for normal. N. Okay, that's the normal. Okay, so here comes that light. And once again, we'll try and do it in we'll do it in black. Okay, so here's that light beam coming in. Coming in like this, it's going to hit there. Okay? Well, here's our angle in. Right there. Just going to put an angle in, angle I, that says. Okay, and it's going to bounce out the same way it came in. So let's show that same line coming out. And it's going to bounce out, and don't forget the final destination is the person's eye. And that looks pretty good. It looks like the angle over here. Let's see where that is. It looks like the angle out. Right there, angle out. Does look like it the same as the angle in. So I think we've got a pretty good symmetry here. So the thing is the same, the light beam is the same coming in, is the in, as it is coming out. I think we've done that pretty well. All right, so where's the butt of this arrow? Well, there's the butt. Okay, and the nose is on the other side, but we only care about the butt. We're trying to find out where his belly button is going to look on the opposite page. So what we're going to do is we're going to take this guy. Let's see. That's a good way to do this. I'll tell you what. I'm going to do it this way. There goes nothing. I'm going to take this very same guy. Okay, watch what I'm going to do. I'm going to take him, and I'm going to flip him like this, so he's straight. Okay, and now he's going back the other way. And what I do, of course, that butt, here's the butt of the arrow, I just flipped it, is going to make it appear when I'm looking at it like his belly button is right there. Well, let's draw the rest of the lines, and we can do that for every spot. If we did it for every spot, that would be his belly button. I'm going to draw him straight coming up like this. Okay, and somewhere over here, let's get it the right height this time, not the other one. I can do it for every spot, and pretty soon, when I'm done, I can do it for his hands and everything else. And when we're done, we would have the exact same image on both sides. Now, this is what we call a plane mirror reflection. Okay? And we did it for every spot. We know that the distance in back equals the distance in front, and that's why I want you to remember it. And I think that'll help you try and work with the plain old flat mirror. But the plain old flat mirrors aren't much fun. Okay? In the next segment, we're going to be doing parabolic mirrors.